So this is an example problem. Granulation of calcium carbonate powder 20 kg per second is performed in a continuous granulator. So the ms dot is given. Powder has a mean diameter of 50 micron and a standard deviation of 5 micron. Its particle size mesh type is equidistance within 0 to 200 micron with 100 intervals. So particle size distribution of inlet has been mentioned, the powdered particles. It flows at 25 degrees centigrade and atmospheric pressure. So all the condition of inlet has been mentioned. Now the first problem, outlet particle size distribution mesh type is also equidistance within 0 to 5000 micron with 200 intervals. Inlet size is 0 to 200, but outlet is 0 to 5000. So the particle size has increased. That's what it means. In the second problem, it says use normal distribution function for outlet PSD with D63 of 100 micron. You know what D63 is? D63 means that 63% of particles will be below diameter of D63. And standard deviation also has been told. Determine the size distribution of the product for both the cases. So that is what you have to find out. Now let us do the problem. For that, we will go to the Aspen Plus window. So let us go to the property estimation. So you have calcium carbonate. But this calcium carbonate will not be conventional. It will be solids. Okay. So we take solid. Press next. We choose solid over here. Next. Run. Okay. Now go to the simulation. First, let us go to the setup, solids, and enter the PSD first. So in the stream class, new PSD, we will say PSD in. So inlet PSD is equidistant What are the number of intervals? Number of intervals 100 and within 0 and 200 micron. So number of intervals 100, zero to 200 micron. Create PSD mesh. So mesh has been created. And then again we will go to solid. New PSD out. So that is the outlet PSD size, which is also equidistant 0 to 5000 micron 200 intervals. Okay. So mesh type equidistant 200 0, 5,000, micron. Create PSD mesh. So mesh type we have created for two different particle size distribution. One we will use with inlet, the other one for outlet. Now we have several stream, binder, hot air, etc. But for the time being, let us delete all of them because we are not using them. So we just delete them. Okay, now we just input the seeds. We have to mention seeds or calcium carbonate as solid, but we are not getting that option because we have to define the stream class of seeds. So for that, first let us go to the stream class and we go to stream and we choose the stream class as mix CLPSD, that is the mixed and conventional solid with particle size distribution. We add both of them this side. And then we go to seed. And here you will find the information for CL solid. So let us go to the CL solid. We give the information. It is 25 degrees centigrade and 1 atmosphere pressure. So 25 and 1 atmosphere pressure, 1 atmosphere, and we have the information that CaCO3 flow rate is 20 kg per second, right? So for that we have to write 20 kg per second and here you have to give the particle size distribution. So here the particle size distribution is PSD in because the inlet particle size distribution we have to put for seeds. So PSD in, and this has a distribution function, and that distribution function is mean diameter of 50 micron and standard deviation of 5 micron. So we will take distribution function standard micron five micron and D50 is 50, and you can calculate this one. So this is the particle size distribution of the seeds. Okay. Now you go to the granulator input. Here you see the outlet particle size distribution option is only open for you because you do not have any binder or hot air, and you have to choose the outlet particle size distribution, which is PSD out. And here you can give the information from 0 to 5,000. The entire region, what is the outlet weight fraction that you want, that information you have to put in Suppose you want 0.02 weight fraction of entire granules to fall between 4750 to 4775 micron, then you just put in the value of 0.02 over here. Likewise, you have to give the information for the entire table. Or else, you can put the values of the particle size distribution using the distribution function. For that, you have to give a distribution ID, and then the distribution function as normal function. It has been chosen as normal function over here, and the outlet PSD with D63 of 100 micron, standard deviation of 10 micron. So that information you can give over here. So normal distribution D63 of 100 micron and the standard deviation of 10 micron. Okay. Now all the inputs are complete. So you can run the simulation. And the results are available. So we can see the results. So directly go to the particle size distribution. So this is how it is. So you can see the seeds and weight grain. Seeds are given by the blue color and weight grains are given by green color. The seeds, they have a lower particle size distribution than the weight grain. Weight grain is having higher particle size distribution. So basically there has been a size increase due to the granulation. And that is how the calculation has been done. Okay. Now this is entirely based on the information that has been given for the seeds and the particle size distribution of the outlet. Okay, we have not used any binder or we have not used any hot air. Okay, now let us go to the second problem, and this is the second example, which says perform a wet granulation in the same granulator by spraying a mixture of glycerol and calcium carbonate. Now here calcium carbonate and glycerol, they have formed a mixture, and this is used as a binder. It is fed at the same condition as that of the solid CaCl3, and you assume the bed mass to be 100 kg. Okay. Now first you have to use the mixed and plug flow granulation model, and later you have to use the agglomeration model with a size enlargement, kernel constant prefactor of this. And the third problem, you will use the superficial gas velocity and default prefactor coefficients. So for first three problems, we are not using any hot air. And the last problem, we will use hot air, and here it is said that fluidizing air is fed at 1 kg per second, 50 degrees centigrade, 1 atmosphere. It was 25 degrees centigrade and it is 50 degrees centigrade. So it is, the air is hotter than the other bed mass. You assume bed cross-sectional area of 0.5 meters square and separation sharpness is 0.75. Here again, determine the size distribution of the product of all the cases, all the 4 cases. So let us solve this problem again. For that, we need to add a few items in the properties, because it is not only the solid calcium carbonate. We have the binder material. So go to specification. You need calcium carbonate, which is conventional. Okay. So we write calcium carbonate. First of all, let us rename it as calcium carbonate solid. Okay, calcium carbonate solid. And then we can write here calcium carbonate. So conventional calcium carbonate will be taken. And then we have to use glycerol. Now glycerol, I don't know whether it is, yeah, it is taken. So conventional glycerol and air. So these 4 components we need. Again we run. Okay, so property analysis is done. Go back to simulation and first of all go to the flow sheet. Here first you have to add binder. We are adding binder over here. Okay. Now go to binder and provide the inputs. What is the binder? Go back over here. Spraying a mixture of glycerol 5 kg and calcium carbonate 1 kg per second. 25 degrees centigrade and 1 atmosphere. Okay. So 5 kg and 1 kg. So it is mass flow rate kg per second. This is 1 kg and this is 5 kg. This is 25 and this is 1 atmosphere. Okay, so the binder is defined. Now go back to the granulator input. So here you will find the 2 options open for you. So first go to granulation model. Granulation model, first cumulative bed mass. What is the cumulative bed mass? It is 100 kg. So add this number over here, 100 kg. And we have to run it using mixed flow and plug flow granulation model. So plug flow is already there. Let us run with plug flow and see what happens. Okay, now there is a problem. So we have to use stream class global as mix CL PSD. That means all the streams that is entering into the block mix CL PSD. Okay, so now you just run the simulation. Yeah, so results are available. Now let us see the particle size distribution once again. Now you see the change in particle size distribution. There is slight change in the particle size distribution. Why? Because the binder mixture is already having some CaCO3, right? So that CaCO3 is getting coated over the solid CaCO3, and that is the reason wet grain is having a different particle size distribution than the seed material. But the residence time may not be that high, so the change in size is very small, but still there is an increase in size. That's what we observe. Okay, so this is by plug flow model. And if we use the mixed flow model, suppose we use surface proportional, okay, then run it, and you see the particle size distribution, it changes. Okay, for plug flow model, the change is not that much, but for mixed flow model, the change is quite wide. Okay, and if you use the volume proportional model, it is higher. If you use adjustment factor, say 1.5, and run it once again for volumetric proportional, you will find still higher. Okay, so you can play around with these numbers. Obviously, it should be logical. Then you will get to know how the granulator performs. Now we go to the next problem, where we assume size enlargement by agglomeration with kernel constant prefactor 1 into 10 to the power minus 10. So we move to the next model, which is agglomeration model. So this is the granulator input, particle growth by agglomeration, bed mass is same, and constant kernel. First let us use constant kernel of this and specify the kernel prefactor as 1 into 10 to the power minus 10 second inverse. So 1 e minus 10 second inverse. Okay, so this is enough. Run the simulation. Okay, we find some warning, probably with agglomeration model with fixed kernel, it is not working. Let us try something else. Let us try with agglomeration model with superficial velocity 5 and default values of prefactor. So for that, we will use determine prefactor flux number. It is 5 meter per second, is it? Yeah, 5 meter per second and default values of prefactor. So for that, we use 5 meter per second and run the simulation. Let us see what happens. Well, again we have some warning result, and the size distribution is not as per expectation. We are not probably feeding in the correct data. Anyway, let us go to the fourth problem. So we have fluidizing air. So we are giving a correct figure of fluidizing air. Now the superficial velocity will be calculated by Aspen plus itself. So let us see whether it helps. So we have to add the fluidizing air. For that, we have to go back to the flow sheet and we add in the so we rename it as gas in and we rename it as gas out. Okay. Now we have to give the properties for gas in. As you remember, it is 50 degrees centigrade and 1 atmosphere pressure. Okay. And 1 kg per second, right? So this is 1 kg per second. So specification of gas input is done. We go back to granulator input. The moment we open granulator input, we find the elutration options are open over here. Because we have given the option for gas inlet, so elutration option is also open for us. And we have to feed in these two data, cross-sectional area and separation sharpness. For that, cross-sectional area is 0.5, separation sharpness is 0.75. So 0.5 meters square and 0.75 separation sharpness. Okay. Now again we run the simulation. It is not giving good result. And granulation model, if we run, then we are getting good result. Okay. And here it is somewhat same as whatever we have obtained for model without elutration. With this, we come to the end of this lecture and we shall come back with some other interesting lecture very soon. Thank you.